Okay, welcome back everyone. In this video we're going to talk briefly about one special case of an electric field, and this is the electric field between parallel plates. And if you were to visualize this, there's much better pictures in your book, but you have a couple of metal plates that are separated by some distance and they have some sort of area, and they're able to maintain a certain amount of charge Q. And so this is kind of a special case that we're not really going to prove, at least this year, but it can be shown that the electric field between these plates is equal to 4 pi times that constant K times Q over the area A. So we're going to use this to solve an example problem, but first let's just talk a little bit about this equation. Hopefully it makes sense that the more Q you have, as Q increases, that the amount of electric field you have goes up. But hopefully it also makes sense that as the area increases, that the electric field goes down because the charge is getting more spread out. So those are just a couple of things to think about. Okay, so in this example, this is number 63 from page 533. This is another 3-dot problem that we're actually going to basically take care of in about a minute. So we have two large parallel plates. They're oppositely and uniformly charged. So if one side is plus Q, the other is minus Q. They don't add up. That's just kind of how these things work. And so the magnitude of that charge is this Q right here. If the field between the plates is 1.7 times 10 to the 6 newtons per coulomb, how dense is the charge on each plate? So when we say how dense is the charge, this is a weird thing we call the surface charge density. And you'll learn a lot more about this next year, but this is kind of a neat little intro. It's got the weird Greek letter sigma because of the S sound for surface, and it's basically the amount of charge divided by the area. Okay, so what we want to solve for is basically Q over A, which is E over 4 pi K. So it's just 1.7 times 10 to the 6 newtons per coulomb over 4 pi, and then 9 times 10 to the 9th, and then that's it. So this turns out to be something along the lines of 15.0 times 10 to the negative 6th. And if you were to keep all the units in this, you would find out that this actually has units of charge, coulombs, over area, meters squared. I'm not going to prove that right now. You just have to get in there with the units of K. And so what this tells us is that this density is 15.0 microcoulombs per meter squared. So there you go, a 3-dot problem in less than a minute.